Okay, so welcome again to everyone. This is lecture number 37 in the course Phase Equilibria. So what we'll do is that we were discussing in the last few lectures about ternary phase diagrams. So we'll just briefly recap of some of the past work and before we move on to the new contents. So basically, we introduced ternary phase diagrams. And in those diagrams, we looked at a few things like, how to determine the composition, what is the tie line, what is the line of fixed composition, what is the horizontal line parallel to any particular sides of the triangle. So basically, ternary that it's represented by these equilateral triangles, and where three sides represent the pure components A, B, and C, and you can determine the alloy composition. By reading from the phase diagram, you can make alloys with a fixed composition of say one element, in this case C. You can have alloys of composition with fixed A by B ratio or B by C ratio or C by A ratio. And then we also introduced the concept of, so first thing was composition, then we looked at the tie line, we looked at application of lever rule, and so on and so forth. And then we introduced the application of phase rule. So and phase rules for ternary systems are slightly different because you have one extra component. So if you have this F plus P is equal to C plus 1, then since you have C as 3, so this is 4, and depending upon the number of phases that are present, you can have degree of freedoms which are ranging from 0 to 3. And so for example, you can have a 4-phase equilibrium. If you have 4-phase equilibrium, then degree of freedom will be 0 for 4-phase equilibrium, and if you have degree of freedom as number of phases as 3, then it would be 1. So this would be 3-phase equilibrium, and degree of freedom will be 2 if you have 2-phase equilibrium, and it would be 3 if you have 1-phase equilibrium. So it would be either liquid or solid state. This would be liquid plus solid, or solid plus solid. This could be liquid plus solid, or solid plus solid plus solid, and this could be liquid plus 3 solids. So this is how. So this is basically the invariant point in a 3-dimensional phase diagram of a ternary system, whereas in this case this F is equal to 1 will give you a line variation, this would give you a area variation, and this would give you a 3-dimensional variation of degree of freedom. So number of independent variables is different in case of different phase equilibria. And then we also introduced the so we first initiated with phase diagrams with 2 phases. So those phase diagrams basically have liquid going to liquid plus solid, and then you have solid as you go down in temperature. Okay. So I mean, examples of such systems could be isomorphous systems. Isomorphous systems where A, B, B, C, and C, A, all three of them make isomorphous phase diagrams, and eventually what you obtain in the case of a ternary system is something like this. So you have, so let's say you have phase diagrams like these. And so the top surface consisting of these liquidus will be the liquid surface, liquidous surface, which is a curved surface, let us say ABC, okay, and then you have this bottom surface, which is the surface which is depicted by this turquoise color. This is the solidus. So, this is the liquidus and this is solidus. And the difference and in between two you will have a single phase region. So, between these two surfaces, these are curved surfaces, you will have two phase region. Let us say you start with liquid, you end up with liquid plus alpha, and between the two you will have liquid plus alpha region in between these two surfaces. So, when you cool a alloy, for example, of a composition X, so you start with a alloy of composition X, this X starts from liquid state, then it slowly starts converting into solid, and as more and more solid forms, just like in a binary solid solution, the solid and liquid compositions, they change along a tie line, and finally the solidification is over into a single phase. However, unlike a binary system, so in a binary system what happens is that, if you recall, in a binary system, as you so I am just going to go across. So, this is a binary system, let us say AB. So, as you decrease the temperature for a given alloy, the tie lines vary like this, okay, as you reach from the start to end of the solidification. So, this is composition C naught. So, tie lines in a binary system, they are flat and they are parallel to each other, whereas in a ternary phase diagram, the tie lines need not be parallel to each other. So, because solidus and liquidus are curved surfaces and the profiles may not be exactly parallel to each other, as a result what will happen is that you will have liquidus going something like this, and then correspondingly you will have some solidus that will go in another fashion, and the tie lines between these two, they may not exactly be parallel to each other, and they may change directions as you go from section to section. So, if you draw three-dimensional sections of so this is tie line in a in a 2D binary system, okay, and they are parallel tie lines. Whereas when you come to ternary system, so if I draw, for instance, again, so let us say this is this is A, B and C, let us say. So, this is let us say the alloy composition X. So, in the first instance what happens is that your liquidus and solidus are something like this, all right. So, this is let us say at a temperature, so we went through last time temperature T1, T2, T3, T4, it is at a somewhere. So, you have temperature T1 greater than T2 greater than T3 greater than T4. So, T1 is the temperature at which solidification begins, and T4 is solidification ends, okay. So, T2 and T3 are the intermediate temperatures. So, if T2 and T3 are intermediate temperatures, then you can draw the tie lines. The tie lines would be for this composition, let us say this is the tie line, okay, and this falls on this line, okay. So, this is your liquid L2 and this is your S2 composition corresponding to, this is solid state, this is liquid state, and this is in between liquid and solid state. Now, as you go to T3, another temperature, as you go down in temperature, the liquidus and solidus moves. So, more and more liquid, the solidus comes closer to X. So, this is your X, let us say, and the solidus is somewhere here, liquidus is somewhere here, and so your liquid region is shrinking little bit, and your tie line may not be the exactly what you see there, tie line could be this tie line, okay. So, this is L3 S3. So, these tie lines may not be exactly parallel to each other, rather the paths may be different, but they do not within at the same temperature, tie lines do not crisscross each other. So, tie lines are they could be a certain angle to each other, but they do not go crossing each other. So, this is how tie line orientation varies in a ternary phase diagram as compared to, and the ends of tie lines are determined by free energy considerations. What is the equilibrium composition of solid and what is the equilibrium composition of liquid. So, you will have to do that, one has to do that exercise. So, you can do that manually, but nowadays softwares are used to calculate these free energy composition diagrams to give you the composition of phases in equilibrium. So, this is how the solidification will proceed. So, you have so if you go back to previous diagram, so in this your if you are plotting the composition, for example, if you are plotting the cooling of solid liquid. So, liquid goes this way and the solid corresponding solid will be at this point, okay. And if you project them on 2D plane, the liquid will show a path like this, the solid composition show path like this. So, you will have these are tie lines, this is first tie line, this is the second tie line. So, if I just zoom it up, let us say I zoom it up little bit, this particular part. So, this is the composition X, and within this composition you have this projection of liquid compositions and projection of solid compositions. So, the first liquid that formed here is somewhere here. So, this corresponds to, so let me just make a little bit of modification, it does not go like this, it goes more like this, okay. So, the first solid that forms is somewhere here, and this is corresponding to this tie line. The second one will form somewhere here, and this is corresponding to this one. So, this is L1 S1, this is L2 S2, and this would be, let us say, the L3 S3, and so on and so forth. That is how the liquid and solid curves will change. So, this is solid composition curve, there is the liquid composition curve projected on the 2D plane within the ternary phase diagram. So, this is how you can monitor the change in composition upon solidification of an alloy within the within a two phase within a ternary system consisting of two phases. Now, let us look at another ternary system. With three phases. So, an example of such a system could be something like what I am showing you here. So, I am not going to go through all of them, but what we are going to do is that we have basically what it means is the liquid L plus 2 primary solid solutions. So, this could be alpha plus beta, okay, alpha and beta, and it gives basically it gives rise to and you have a eutectic reaction, liquid giving rise to alpha plus beta. You can have peritectic also, but we are going to discuss the eutectic in this case for the sake of simplicity. So, the phase diagram looks something like this. Okay, this is the phase diagram. And this, all right, and let us now build a phase diagram. On this side we have phase diagram which is like this, let us say. all right. On the other side we have another phase diagram which is of this kind, let us say. Right. Okay. And then we have a phase diagram on this side which is something like this. So, if I take components, sorry, let me just, so if I take component x, y and z, then between x, y I have a eutectic reaction, and between y, z I have a eutectic, and between x, z I have isomorphous. Isomorphous system. So, we have various surfaces here. Let us say I identify them as A, B, and let us say what is C, this is C, and then we say this is point D, we say this as point E, and this is point F, and this is point G, right, and then we have somewhere point, so we can draw a few lines here. So, this could be, for example, point M, this could be N, okay. So, M, N, and we can draw some internal boundaries as well. So, internal boundaries could be, for example, drawing this point to this point. Similarly, we can draw this point to this point, okay. And we take an alloy composition, for instance, some value x, okay. So, this is the C naught, let us say, okay, the composition. So, basically what we see is that these curves that we have, for example, in this case Mn, so this you have various things here. So, what is the liquidous surface here? The liquidous surface would be A, M, B, N, what is this, C. So, this is the, so if you look at the top part, which is the liquidous surface, let me just draw the liquidous using a different color in this case. So, this would be, these are the bounds of liquidous, okay. Right. So, these are the bounds of liquidous, and in between you have this. So, you have one region which is A, C, N, M, another region which you have is B, N, M. So, A, C, N, M and B, N, M, these are the liquidous surfaces, two segments, and they are joining each other at Mn. Now, in this case we have shown Nm to be going down, but it is possible that Nm may achieve a maximum as well. Now, in between somewhere you have these other surfaces as well. So, you have so this is this Mn, let us say, is in this case is the sort of valley or eutectic, in this case it would be curve for a ternary system. So, and then we have other curves like DG and EF, So DG and EF, they join the points below which solid phases occur. Okay. So these are the points of so this basically they are the compositions of alpha and beta phases that you might have in the eutectic reaction DG and EF. So this, for example, would be, let's say, alpha, this would be alpha, this would be beta. So they join the compositions, and then surfaces, another surface that you have is AD. So you have another surface which is A. So you have AD, G, and then you have C. Okay. So you have surface A DGC, and another surface you have BEF. On the other side, BEF. These are the surfaces which they form the solidus. So they basically separate the two phase liquid plus solid region from the solid region. So basically these are the various surfaces and boundaries which separate liquid plus solid, solid plus liquid, liquid plus solid from the liquid plus solid from the solid regions. So and in between you have these solvers. So for example, this would be the solvus boundary. So this would be the solvus G. So if you plot, for example, here D prime and G prime, so D prime G would be the solvus which separates a solid from each other. So that is how we describe a ternary phase diagram consisting of these two eutectic and regions. Now we see that the curves, for example, MN DG as well as EF. So you can see MN, this is MN, DG and EF. They do not necessarily lie in the same plane. They will most likelihood they will not lie in the same plane if the eutectic temperatures are different. Okay, they are in okay, and the curve MN in this case, so the curve MN, this lies above the surface, this DEFG, sorry, DEFG. Yeah. So this DEFG is the surface which separates the solid region from the two phase region. So MN lies above this. All right, and then you have so basically there are three curves. You know DM NG, MEFN and DEFG. So you have DMNG and then you have MEFN and then we have DEFG. These are the three surfaces which basically enclose the three phase space consisting of liquid plus two solids, and that is how you essentially draw the compositional landscape of a composition temperature landscape of a ternary phase diagram. Now how does it look like for you if you take alloy of a given composition? How does it, for example, look like at different temperatures? So when you draw, for example, you take an alloy of a composition X, C0 in this case, and as it goes through the solidification, as it goes through solidification at various temperature, how do the sections vary? So sequential variation phase evolution, so variation in types of phases as you go on decreasing the temperature. So you may have various scenarios. So for example, in this case, one scenario could be, you know, so it's not going to be very exact as compared to the according to the phase diagram that is drawn, but this is just a schematic. Okay, so So, for a given composition, let us say at a temperature T1, you have a section like this. So, of course, we are not going to go for composition, we are just going to go for the sections. So, let us say we have something like this. So, this is at a temperature T1, this is let us say X, Y and Z. So, you have alpha plus liquid, you have liquid plus beta, and then you have beta. So, basically you are at a temperature where you are in partially solidified state, so that you have on the boundaries you have alpha plus beta regions. So, if you take a, for example, a section along this, if you take a section along this, starting from pure Y to let us say some ratio of X and Y, you will have a binary phase diagram just like what you see. So, it will be a binary phase diagram between pure Y and some ratio of X's to Z. As you decrease the temperature further to T2, let us say, the phase boundaries will move because the phase fields, the width of the phase fields changes. Okay, so, if you go to T2, it might change, something like what I am showing you here. Let us say you have a situation like this. So, this is again X, Y, Z. Let us say this is phase field beta, this is phase field liquid plus beta. So, this is alpha, essentially alpha phase field is broadened, this is liquid plus alpha, this is liquid, this is alpha plus beta, and this is alpha plus beta plus liquid. So, these are different phase fields. You can see that this is a point which is 3 phase point. Okay. So, if you fix so you have only 1 degree of freedom. When you have only 1 degree of freedom, you can only change the composition or the temperature. So, if you have fixed the temperature, then you can vary the composition along the line. So, this is for instance, in this case the point at which you have 3 phase equilibriums that is existing. So, as you decrease the temperature further, you will have broadening of these phase fields, solid phase fields. For example, at a temperature T3, you might have a situation where alpha has broadened further, and liquid has really shrunk. So, this is for instance beta, this is alpha plus beta, this is alpha, and somewhere in between you have tiny phase field here as liquid, then you have liquid plus alpha, you have liquid plus alpha plus beta, and then you have liquid plus beta. So, this very tiny phase fields here is liquid, and when you come to very low temperature below the solidus, so here you are below the solidus, you are now slowly approaching the solidus surfaces. So, your liquid phase field is shrinking and solid phase field is expanding, whether it is alpha or beta, it depends upon where you are, what kind of phase diagram you have. So, eventually what you have is you have alpha plus beta and then beta. So, this alpha phase, you can see that sequentially you started from liquid with surrounded by liquid plus solid surrounded by terminal solid solutions. As you decrease the temperature further to T2, so T1 is greater than T2 is greater than T3 is greater than T4. So, this is T4. Okay. So, you can see that your alpha plus beta two-phase field has started forming, the liquid shrunk, and there is an increase in the areas of two and three phase fields regions, with some expansion in the single phase field regions. And as you went down in temperature further, your two phase fields and solid phase fields have increased in size, and liquid phase field has shrunk in size, and as you come down to T4, the solid phase field has expanded. So, this is how the microstructural evolution takes place in a ternary phase diagram. You can draw these lines like sections. You can take isoplates and evaluate the phase evolution sideways looking at in a binary system. So, this is how the phases will evolve in a ternary system. So, we will not get too deep into ternary systems. We will close this discussion on ternary systems here, and I would suggest that for further reading on ternary phase diagrams, as I suggested, you should read the book on this ternary phase diagrams in material science. By D.R.F. West and N. Saunders. This is a very good book. It has a lot of ternary phase diagrams for different alloy systems. For various systems, and it gives a very good flavor. It also has some exercises which you can do and work out. So, we will close here this lecture. What we have looked at is the ternary phase diagram consisting of three phases. Of course, you can go further to four phases, it gets more complicated. We will probably touch upon that in the next lecture, and then we will move on to the next topic. Thank you very much.